Welcome to this explainer. Today, we're taking a really hard look at a topic that consistently, and I mean literally every single exam series, acts as a massive roadblock for math students. We're talking about integration by substitution. Specifically, we're diving deep into the Cambridge AS and A-level mathematics syllabus, code 9709, section 3.5. Now look, if you're preparing to sit for this exam, mastering the actual mechanics of this exact topic is completely non-negotiable. But here's the thing, we aren't just going to look at standard formulas today. We are going to completely deconstruct the psychology of the exam itself. To help map this out, let's picture two very common mindsets that candidates fall into. We'll call the first approach the Alex mindset. Now, Alex relies entirely on raw memorization and basic data inputs. Alex is fast, gets the numbers down, but completely misses the deep analytical links. Then we have the Sam mindset. Sam grasps the big picture, constructs really persuasive mathematical arguments, but frequently misses the explicit restrictions set by Cambridge exam command words. And guess what? That drops vital method marks. So we're going to use these two contrasting approaches to figure out exactly how to secure those elusive top-tier mark bands. I want you to listen to this. Cambridge senior examiners explicitly state in their global reports, examiners report that 3.5, integration by substitution, is one of the most misunderstood areas in mathematics. I really want to let that sink in for a second. This isn't just a slightly difficult topic. It is universally misunderstood across the globe. Why? Well, the reason so many candidates struggle here is because they approach integration by substitution as a simple mechanical swap of variables. They treat it like a really low-level algorithm. Just change an x to a u and you're done, right? Absolutely wrong. Cambridge examiners are not just looking for a final numerical answer at the bottom of the page. They are actively hunting for a highly structured analytical process. When you sit in that exam hall, the paper is fundamentally testing your ability to handle causal relationships between changing variables. So by the time we finish this explainer, I am going to show you exactly what the principal examiners are looking for on their highly specific marking grids so we can fix this misunderstanding right now.
So, here is the exact structural blueprint we'll be following today. 1. The integration challenge. 2. Decoding objectives. 3. The 5-step procedural framework. 4. Spot the examiner trap. And 5. The ultimate exam strategy. Let's get right into it.
Section 1. The integration challenge. There is a massive, and I mean massive, divergence between what students think they need to write down and what the Cambridge framework actually demands from them. The core tension really lies between superficial mathematical breadth, which is basically just trying to memorize every possible integral variation you've ever seen, and the analytical depth that examiners actually reward with marks. Integration by substitution isn't just plugging in u. It's actually a theoretical architecture. It relies on extremely precise definitions and causal relationships to transform and evaluate complex integrals. Think about it like this. When you substitute x for u, you are fundamentally altering the dimensional space of the entire problem. You're creating a strict causal relationship where changing the variable absolutely necessitates a precise change in the differential. Your dx literally must become a du. And crucially, this is where so many drop marks. Your integration limits must also transform to match this brand new architecture. You can't just leave them behind in the old x dimension. Let's bring back our two students to see how this plays out in real time. Consider two different ways to tackle a really complex substitution problem. The first approach, the Alex mindset, relies purely on raw factual inputs. Alex's instinct is to just quickly state the formula, define u, calculate a quick derivative, and plug the raw data back into the equation. To Alex, it feels like getting the job done efficiently. Alex is sitting there saying, look, I got the right number at the end, I'm moving on to the next question. But then we have the second, much more analytical approach, the Sam mindset. Sam recognizes that this raw input is simply not enough for Cambridge. Sam fights to build what we call an analytical thesis link. This means Sam explicitly writes down the mathematical relationship. Sam notes that changing the variable to u alters the entire domain, which is exactly why the upper and lower limits have to be recalculated before any integration actually happens. Now, think about the examiner marking this. The examiner only knows what is physically written on the page. They can't read your mind. Documenting that causal relationship step by step, the way Sam does, is exactly what elevates an answer from basic, low-tier factual input to the analytical depth that completely unlocks those top-tier A-star bands.
Section 2. Decoding assessment objectives.
Now, to really maximize your performance and stop leaving marks on the table, it is absolutely crucial to understand how your math is actually being assessed behind closed doors. The academic benchmarks for this Cambridge syllabus target 3 very distinct cognitive domains. Domain 1 is knowledge and understanding. This is your foundational recall, knowing your standard integrals right off the top of your head. Domain 2 is application. This is taking that raw knowledge and actually extracting the relevant data from a messy question to correctly set up your substitution. But Domain 3? This is analysis. This involves highly logical, structured reasoning. It's verifying those causal relationships we just talked about and drawing evidence-based conclusions. And here is the golden rule you have to remember. The higher the mark value of a specific question on your paper, the more heavily it leans on this third domain. A 7-mark question isn't testing Domain 1, it's heavily testing Domain 3.
So, how do examiners actually trigger these different domains? They do it through specific command words. And misinterpreting these is a massive trap. For instance, if a prompt uses calculate or find, the assessment is skewed towards that second domain, application. But there's an explicit restriction here. You must show your working step by step. If you just magically produce a naked final answer from your calculator, you get heavily penalized. On the other hand, if the command word is show that or verify, we are moving fully into the analysis domain. Think about this. When a question says, show that the integral equals 5, the final answer is actually already known. It's literally in the question. So 100% of the value of that question lies in the method marks. If you skip steps, you get 0. And finally, if you are asked to evaluate, you absolutely must provide mathematical justification and explicitly state any limitations or assumptions. Misinterpreting evaluate as simply calculate triggers an immediate, painful penalty on the examiner's grid.
Section 3. The 5-step procedural framework. Strategy check. Before we unlock this top-band framework to help you absolutely crush your upcoming exam sessions, I need to make sure your revision feed is perfectly optimized. Take a second right now to subscribe to Ace the Exams at the handle @AceTheExams and enable all notifications. You do not want to miss our weekly Cambridge exam breakdowns, whether you're sitting for IGCSE, O-levels, or AS and A-levels. Okay, let's deploy the matrix. When you inevitably hit a structural roadblock mid-calculation, it massively helps to rely on a universal framework. Here is a foolproof 5-step procedure for tackling 3.5 integration by substitution and absolutely guaranteeing you capture every single method mark. Step 1. Deconstruct the question. Immediately highlight the command word we just talked about. Step 2. Extract relevant data. Identify your complex function and choose the absolute most efficient U substitution. Step 3. Select an analytical framework. Establish your du/dx and strictly set up the framework for changing those integration limits. Step 4. Execute with clear notation. Ensure your integral signs, your dx, and your du are perfectly mathematically aligned. And Step 5. Present with correct terminology. Draw evidence-based conclusions that match the specific context of the question.
Let's watch our 2 scholars rewrite their work out loud using these higher-order execution requirements. They need to engineer a flawless, top-tier response block. Applying this means looking at step 1 and 2 together. Alex correctly says, okay, let's let u equal the inner bracketed function, and executes a clean derivative. Great. But then, for step 3, Sam steps in to justify the recommendation. Sam explicitly writes down, since x varies from 0 to 2, substituting these into our u equation means u now varies from 1 to 5. Do you see that? They are evaluating the alternative boundaries right there on the page. For step 4, the execution requires rewriting the entire integral strictly in terms of u and du. Sam double-checks Alex's work to ensure there are 0 x variables left behind. None. Finally, presenting with terminology involves performing the actual integration, substituting the new u limits, and stating the final evaluated area, potentially even linking it to the geometric space it represents on a graph. This entire collaborative process shifts the work from basic descriptive math into high-level comparative analysis.
Section 4. Spot the examiner trap.
All right, it's time for an interactive workshop. Let's put this into practice and adopt a highly analytical tone. I'm going to put a metaphorical 60 seconds on the clock. Read the sample integration block carefully. Our sample student correctly identifies the substitution u. Perfect. They correctly find du dux. Awesome. They substitute u into the main function perfectly. At first glance, this looks like a solid A-grade response, right? But look really closely at the transition line between the substitution phase and the actual integration phase. Do you see the flaw? Did you spot it? The exact point of failure is where the student writes the new integral in terms of u, but actually retains the dx differential at the end, along with the original x domain limits at the top and bottom of the integral sign. Even though their final numerical answer somehow ends up completely correct, probably because they just typed the original equation into a graphing calculator, the examiner will instantly penalize this. Mathematically speaking, integrating a u function with respect to x is a completely different, frankly nonsensical operation.
The logic is fundamentally flawed, and the method marks drop to 0.
And that exact mistake leads us right into the top 3 examiner alerts, pulled directly from global Cambridge grading reports. Alert number 1, confusing cause and effect with terminology. If a substitution causes a domain shift, you must state it explicitly. You can't just assume the examiner knows you know it. Alert number 2, forgetting format and presentation checks. Just like the trap we literally just analyzed, dropping the dx completely or wildly mixing x and u variables in the exact same integration line severely bleeds marks. It shows a lack of theoretical understanding. And alert number 3, answers lacking context specificity. Your final mathematical evaluation must tie back to the original question. If an exact value is requested, giving a rounded decimal without justification instantly fails that context check.
So, mapping a correction pathway out of these incredibly common traps requires strict, unwavering compliance. Let's use a digital highlighter approach here. When a student mistakenly shows mixed variables, like writing an integral with both an x and a u trapped inside it, the absolute expectation from the examiner is strict algebraic separation. The correction pathway here is implementing a hard, unbreakable rule for yourself. Do not draw the integral sign again until every single x, including the differential dx, is fully and completely translated into the language of u. And when limits are left undefined, the expectation is visible limit translation. The fix is so simple, but so effective. Physically write a mini table on the side of your exam paper showing the old x values pointing to the new u values. Writing down these explicit comparative connectives physically forces the examiner to award you those crucial high-band method marks.
Section 5, the ultimate exam strategy. Let's talk about a memory hack. To guarantee you can actually execute this level of analytical depth under extreme ticking clock time pressure, it really helps to use a visual story method. The big breakthrough here, the realization that Alex and Sam finally come to, is that simply knowing the integration formula isn't enough. It's the clear presentation of causal relationships where the points are actually hidden. So imagine the original integral is a complex machine operating entirely in x space. The substitution u isn't just a letter, it is a universal translator. To use this translator correctly, you can't just translate the main text, meaning the function itself. You also have to translate the punctuation, which is the differential dx, turning into du. And you have to translate the cover pages of the book, which are your upper and lower limits. If you leave any single part of the original x space behind, the entire translation fails. Keeping this visual story in mind helps encode the entire conceptual process, preventing those critical, easy-to-make omission errors when you're 3 hours deep into a paper and heavily fatigued. Let's distill everything we've covered today into 3 overarching universal operational rules. Consider this your ultimate pre-exam checklist. Rule 1 is the 3-step question scan. The moment you open that exam paper, do not just start calculating blindly. Decode the command word first. Identify the assessment objective they are actually targeting, and mentally map out those causal relationships. Rule 2 is the marks per minute formula. Always look at the point value of the question. If it's a heavy 7-mark question, you must allocate specific, structured time to write out the full analytical framework. Write down the domain limits, show the derivative setups. Don't just rush to the final algebra. You are actively farming method marks here. And Rule 3 is the post-writing compliance audit. Before you flip the page, do a rapid 10-second visual scan of your math block. Are your variables mixed up? Did you accidentally drop a differential? This rapid audit catches the top examiner traps before they can permanently damage your final grade.
You now possess the exact architectural blueprint to completely dominate integration by substitution. You know exactly how to bypass those raw factual input traps, how to flawlessly leverage the 5-step procedural framework, and how to secure those top-band analytical method marks. Remember, Cambridge isn't just about finding the right numerical answer, it's about conclusively proving the logical validity of your mathematical translation from one dimension to another. The next time you see a complex integral staring back at you on an exam paper, ask yourself, are you just blindly crunching numbers, or are you actually speaking the precise language of the mathematics? If you found this breakdown valuable, you need to subscribe to Ace the Exams at Ace the Exams right now. Hit that notification bell so you get our weekly grade masterclasses, and drop a comment below sharing exactly which Cambridge subject and level, whether it's IGCSE, O-level, AS, or A-level, you are preparing to conquer next. Let's get to work.